Welcome. This is the final presentation for the SuperRes Cryo-EM CS Plus group. My name is Xiaozhen Du, and I will be presenting alongside Reid Chen. Also in the project are our graduate mentor, Qingwen Huang, and our faculty mentors, Dr. Alberto Bartaseghi and Dr. Cynthia Rudin. First, what is Cryo-EM? Cryo-EM is a Nobel Prize-winning imaging method which is used to image biomolecular structures such as proteins at near atomic level. Being able to see proteins can help determine how they function. Recognizing protein structure and function is essential for scientists trying to design better drugs to tackle some of the world's most devastating diseases, including HIV, cancer, and most recently, SARS-CoV-2. Using Cryo-EM to obtain a 3D protein structure or 3D reconstruction is a lengthy procedure. First, the burst images, a series of which constitute a movie, are taken. The movies are aligned and averaged, resulting in a micrograph containing many protein projections. Because aberrations in the electron microscope distort the image, the CTF, or contrast transfer function, which describes the aberration, is fit in order to remove the distortion. Next, protein particles are picked out. After classification, normalization, they are then used for 3D reconstruction. In recent years, large improvements in Cryo-EM resolution are the result of direct application of direct detection devices, DDD cameras, which collect bursts of frames. These developments do not come without challenges. 1. Frame alignment. Individual frames are very noisy because there's a limit on the electron dose used for imaging. Think of taking pictures in very low light conditions. Number 2. Using electrons damage the sample. As such, for later frames, the higher resolution features or the details of the protein are lost. Hence, we will have to compensate for that by relying more on earlier frames for higher resolution features. Overall, we see multi-frame super resolution, which takes low-resolution frame bursts to reconstruct a higher resolution average as a potential solution to these challenges. However, there are also challenges associated with super resolution. To expand on the discussion from the previous slide, accurate frame alignment is critical. If not, high-resolution features will be lost. Yet large amounts of noise make both supervised and unsupervised machine learning approaches difficult. Cross-correlation, or CC, is a traditional quality metric for aligned frames. If you look at the formula below, CC is roughly the dot product of the projection image with the particle image. It measures how similar the particle is to the reconstruction. Yet, cross-correlation is not perfectly reliable due to large amounts of noise during the reconstruction process. This can lead to overfitting. Furthermore, traditional super-resolution techniques rely on a ground truth for the training process. And since the reconstructed volume can't serve as a ground truth for frame alignment, it's difficult to do super resolution with Cryo-EM. To combat these challenges, we've developed a three-step plan for multi-frame super resolution. Step 1. Create a regression model to assign quality measures to aligned frames. Hopefully, this model will smoothen out the overfitting and quality scores measured with the cross-correlation metric. Step 2. Design an alignment model that has a loss function based on a regression model with the goal of achieving better alignments to preserve more of the higher frequency information and achieve super resolution. Step 3. The alignment is done on a finite grid by upsampling our images, and we compare the 3D reconstruction obtained through our alignment method with that of the baseline obtained through the traditional pipeline. We use an apoferritin dataset consisting of 10,000 particles. The protein reconstruction is shown on the left, and the showcase of our particles is on the right. We don't see much difference between the high, medium, and low quality images using the naked eye, especially for high pass, low pass, and power spectrum images. We hope that the CNN can do better.
We started working on the regression model, which would predict the quality scores of images so we could later use it as an objective function. We wanted to replace the current cross-correlation methods with a neural network because we hoped that the model would have a regularizing effect, reducing the overfitting that is present in cross-correlation methods. Using a neural network also has the added benefit that they are fully differentiable, so we can apply gradient descent to our alignment or super resolution models. Because our goal was super resolution and surpassing the Nyquist frequency, the images of the proteins were downsampled from 512 by 512 to 128 by 128 pixels. This was done because at the original resolution, factors such as noise and reconstruction loss prevented us from even reaching the Nyquist frequency. For the labels, we use the sum of 4 quality metrics that mainly use cross-correlation. On the right is a graph comparing the predictions of our final regression model with the labels, as well as each individual quality metric that make up the label. For the regression model itself, we tried several different models. We had observed high overfitting in many of our models, which led us to believe that the neural networks were learning the high-frequency, extremely noisy information rather than the more reliable, lower-frequency information. Because of this, we created a new dataset that passed images through various low-pass filters. For each image, we had 3 filtered images, one containing only low-frequency components, another containing low and middle-frequency components, and the last containing all but the highest frequency components. These filtered images are shown in the figure, with the top row containing only the high-frequency data, and lower rows containing lower frequency data. We first created a growing CNN that would first train on the lowest frequency data, then add a new convolutional layer, and then train again on the higher frequency data. This would be done iteratively until the model had been trained on all the filtered images. The reasoning behind this is that the model would first learn the low frequency information and slowly be fine-tuned on the higher and higher frequency information. In practice, however, this did not perform as well as we hoped, in addition to being computationally expensive. We also trained another network that would add in the higher frequency data in later layers of the network, somewhat similar to a residual network, and this gave us our lowest MSE of 0.051. Since we wanted our network to essentially perform the same function as the current algorithms, which rely mostly on cross-correlation between the image and the projections, we also tried another approach where we fed both the projections and the aligned images into the model. We took the projection and image and fed each of them through their own CNN before concatenating the outputs and putting them through a multi-layer perceptron to get the predicted score. While this gave us good results during evaluation, a major problem with this approach is that when shifting the frames during alignment, the realigned frames will produce a different reconstruction and thus different projections. Because of this, we did not use this model for alignment. The regression model we finally chose for alignment was composed of convolutional layers for downsampling and 8 residual blocks with a fully connected last layer. The model also used only the original unfiltered image as the input. This and the use of convolutional layers with a stride of 2 for downsampling before the residual blocks and fully connected layer greatly reduced the computation time, which was critical for the alignment model where multiple predictions are made for each frame shift. Using this model, we achieved a MSE of 0.057, slightly higher than our lowest of 0.051. But looking at the graph comparing the predictions with the labels, we decided that this model would perform well enough for the alignment model.
We perform alignment at the super resolution level for each of the 10,000 particles in the hypoferritin dataset. Each particle consists of 50 frames, and each frame is upsampled from 128 by 128 to 256 by 256 pixels. In one alignment iteration, we start from the first frame while keeping the other 49 frames fixed. We move the first frame to each of the 9 possible positions, the origin, as well as the 8 adjacent pixels. We chose 9 possible positions because the frames were already initially aligned at a lower resolution. At each position, we take out the average of the frames and score using the regression model. We fix the first frame at the highest scoring position and move on to the second frame. We repeat this process for all frames and that makes up one alignment iteration. We took a total of 2 iterations to reach convergence. Next, we perform a 3D reconstruction with the super resolution aligned particles. The quality of the reconstruction is measured using Fourier shell correlation, and the higher the curve, the better the quality. We have the green curve as our baseline. It is obtained using the standard reconstruction pipeline. Compared with the baseline, our alignment model did not perform as well, as shown by the curve in orange. We believe it is a result of a greedy algorithm not taking into account the uncertainty of a regression model and thus overfitting. We made a small change to the alignment process. When aligning each frame, we only shifted the frame to a new position if the score at that new position is greater than the existing score plus a score delta, which accounts for the uncertainty in our regression model. With that, we did achieve a better score than before and matched the baseline, which is the green curve. There was no improvement over the baseline. We conjectured this was because the score differences between individual frame shifts were too low to provide a strong enough signal to guide the alignment model. As a result, the alignment model did not make many frame shifts.
This project was focused preliminary work and using super resolution principles to improve Cryo-EM resolution. The regression model looked promising, but the alignment model was unable to improve the resolution. This may be due to several reasons. First, the low SNR of the images made training difficult, resulting in a regression model that was not perfectly accurate. In addition, the score differences that resulted from single frame shifts were not large enough to pass the score delta, so very few frames were actually shifted during alignment. Future work can be done in fine-tuning the regression and alignment models. For the alignment model, we could group frames into groups of 5 or 10, so that each movement will give a larger score change. We could also take a step back and test the model by purposely misaligning the frames to see if the alignment model is able to move the frames back to the original correct position. Additionally, the regression model can be used for other purposes. For example, it can be applied to single image super resolution by adding the model to a SR GAN as an additional loss component for the generator. It may also be easier to do regression at the micrograph level due to a higher signal-to-noise ratio. My graduate mentor has started work in this direction and has achieved more favorable results than what we have reported here. Overall, there are still many areas for investigation, and despite being unable to improve upon resolution, there is much room for improvement. Thank you.
Thank you.